Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, welcome back everyone. Hope you had a good break. Went away somewhere. You noticed the weather warmed up and then it got cold again this morning, -3 this morning, so, you know, something about that coming back to uni. All right, so let's get started. So most of you are probably wondering what's happened with the assignment one. So I hope I'll be able to get the marks back to you in the next couple of days. So I have help marking it, and the guy who's helping me, one of our PhD students, very good bloke, but he had a car accident last week which set him back a couple of days, so that's why we're delayed a little bit. I had hoped to get them back to you today, but anyway, someone rear-ended him and that was that for the end of last week. So anyway, so when I do get them back, let me explain how it'll work. So what I'll do is I'll put marks and feedback up on Wattle, so you'll go into the gradebook on Wattle, you'll be able to see the marks and the feedback that's there. We'll then put the assignments that you handed in a binder and put them up in the filing cabinets in CBE on the top floor, on the 4th floor. Again, the way it's marked is it's done on a spreadsheet, and so you'll get marks in various categories that'll break it down, and then you'll get some individualised feedback that is on the grade book, okay? And then what you get back will look just like what you handed in, because it's not done using pen and paper, it's all done on a spreadsheet, all right? So just that's how it'll come back to you. What I'll also do then, because people, you get your own feedback and you get your own mark, but you don't see anybody else's, and that's, the great private world in which we live these days. When I first started teaching, when we gave assignments back, we just put a note on the lecturer's door with everyone's grade on it, including names back then. And then, as privacy laws kicked in, the names were changed to student numbers, and then people worked out that everyone knows everyone else's number, and now everything's very private. So, which is cool, but people want to know how they did relative to everyone else. So once the marks are back on the grade book and you get your mark, at the beginning of one of the lectures, probably for the first 15 minutes, I'll talk about the assignment, I'll talk about what was done well, what was not done well, and I'll tell you what the average was and all that. And relax you basically, because when you get marks back on an assignment where there's no exam, you can't expect everyone to get an HD, it's just not how it works, right? So the marks you'll probably get back and think these don't look like assignment marks, because assignment marks are generally inflated to hell. And these will look like, marks that are, they're designed to put everyone on a reasonable curve, okay? So they'll be a bit lower than you might expect, but we'll talk through that. And what I don't want to have anyone come and say to me at the end of that discussion is, oh my God, I failed. I don't think anyone's failing, okay? But we'll talk through that when they come back. I just want to give you an update on where that's up to, and I apologise they're not back today. But yeah, you can blame someone on Barry Drive who didn't notice the brake lights coming on in the car in front. Oh dear, anyway. All right, okay, so we're back together for another 6 weeks. As you probably know from all your other courses, the last 6 weeks of semester, it's like running downhill. It just gathers speed, and then the whole thing ends in a big rush. Because we don't have an exam, we don't have to do that, so we're going to try and maintain the pace we had, and we're not going to accelerate near the end just to get stuff done. I think we're on track pretty much. So I am going to try in each lecture to do something interesting. I've got a few new links up here today to some web pages that I think you'll find interesting. We'll talk through the first one of these, and we'll actually look at the other ones as we go through some of the material a little bit later. This is a really cool paper. You might remember that early on in the semester I showed you Anscombe's data. This was the 4 different data sets that all looked different, but which all had the same regression output. Same coefficients, same ANOVA table, same everything in terms of numbers, but then of course as soon as you looked at it you saw that one was linear and one was curved, and one had an outlier and one had an influential point. They're all different. Well, you know, you give this stuff to computer scientists and they go absolutely nuts. This is what I call Anscombe's data on speed. So some computing guys worked out an algorithm to create synthetic data sets, artificial data sets, that all had the same regression output, but which all look different. And you can see it's wacky. So here's the Anscombe's data, right? So you can sort of see, we looked at this earlier, linear, curved, outlier, influential point. This data set's been around forever, since the 1970s, right? It's hauled out in every regression class. But you know, people say, well, you know, that's pretty boring. It's XY data, who cares? Well, look at this. This is what these guys have been able to do. All of these data sets that you're seeing here in front of you have the same regression output, the same X mean, the same Y mean, the same standard deviation in X direction, Y direction, same correlation, okay? And of course everyone's favourite is this guy, right? The Tyrannosaurus, right? This data set has exactly the same regression output as this one and so on. So it's pretty cool. They talk about how they did it, which is interesting. I mean, unless you're in computer science, you probably won't get a whole lot of it, but that's pretty cool. You'll notice as the data sets change, the statistics are the same up to second decimal place, and then they start to get messy a bit. And it's that little mess at the end that allows you to do what they've done. And so you can sort of see all the different output here. Oh, it's pretty cool. And a really nice visualisation about what's going on. So I thought I'd show you that. Not in the expectation that we're going to actually use any of this, but just because it just shows you how misleading statistics, particularly the standard things like means and standard deviations, can be if you don't ever look at the data. And so this is the classic example of why you need to look at the data. So I thought I'd show you that one. So I put the link up here on the fun links part at the bottom, and you can have a look at that. All right, back to the fun. Oh, sorry, that was the fun. Back to the stuff. So we've been talking about now multiple regression, so we're in higher dimensions. And I think at the end of the last lecture, we sort of got to the position where you have this data set, very small data set. It's only got 13 data points, but you've got 5 variables. You've got amount of heat, which is the response variable, and you've got 4 chemical constituents of cement. And the idea is to see how the composition of the cement, which is all this stuff down in the lower right-hand corner, impacts the heat, which is that top row. And we talked through this about how, well, you can see that each individual graph, you know, Y versus X1, Y versus X2, each individual graph shows a relationship. And so you sort of think, okay, there's something pretty simple going on here. When you increase X1, Y increases. When you increase X2, Y increases, and so on. But then when we fit a model to this, we realised pretty quickly that it didn't work out quite the way we would expect, because when you fit the model, the coefficients of the X's, one of them didn't have the right sign, right? One of these ones that should have had a negative sign had a positive sign, right? And that's weird. And the reason that we elicited for that at the end of right at the end, before the break, you probably don't remember this, 2 weeks ago, right? Who remembers what happened 2 weeks ago? The word that came out was multicollinearity, right? We think that the X's are collinear, that is related to one another, okay? Now, multicollinearity is a very long word. You'll win Scrabble with it, but most people don't know what it really means. And what does it mean? Well, it's an odd thing. It means that the X's are linearly related in some measure. And it also means that you can't necessarily talk unequivocally about which X does what, right? So here's how I want you to think about regression. Regression is all about taking a response variable and explaining it in terms of what's going on with regard to a number of X variables. Now, simple linear regression is like a fantasy land, because you have one X and one Y, and when you change that one X, Y changes, and you can be pretty clear about how changes in X correspond to changes in Y. Very careful not to use the word cause, but they're correlated with changes in Y. And so you can sit there and say, look, if I increase X, then Y will go up. That's it. 2 dimensions, easy peasy. right? 4 dimensions for x makes it much harder because we can no longer unequivocally say that if I raise x3, y will go up, because when I raise x3, x1, x2 and x4 might all change and y might go down when I thought it might go up, and that's why you get that negative coefficient where you expected a positive one. All right? Okay, so that's all in statistical jargon. How do you say it in sort of plain English? Well, the game for regression is pretty simple. You want to know which x is responsible for changes in y and how. Because your small brain, like my small brain, this is not an insult, everyone's got a small brain, is desperately trying to work out how to partition those changes, right? People want simple answers. How does y depend on x1? Okay, how does y depend on x2? We don't want something complicated like how does y depend on some weird mesh of the x's. So what multicollinearity does is it prevents you doing that simple parting it out. You can't say which x is uniquely to blame for what's going on with y. Okay? And we saw this when we actually fit that model. So if I go and I fit the model to this, we looked at this last time, but I'll just show you again. We got this output, okay? So, yep, positive coefficient, yep, positive, yep, negative, yep, positive, Right, this one looks troublesome. So that's what I was talking about. And if you look at your p-values, remember, we don't like using p-values necessarily, but if you look at your p-values and you take the view that a p-value smaller than 0.05 means you've got a significant result, what you see is not significant, not significant, not significant, not significant, not significant. It looks like nothing is significant. And yet you see a pattern. And that's really disturbing, right? Because the output's telling you nothing's going on and your eyes are telling you something's going on. And that's a problem. And the reason for that is that each of these tests here are what you call marginal tests. In other words, this one says there's nothing going on with x4 if x1, x2 and x3 are already in the model. In other words, it tells you that x4 doesn't add anything once the others are there. If they're not there, x4 works pretty well. I'll show you. Let's fit a model that only has x4 in it. Okay, so let's go summary lm y tilde x4, just x4. Well, x4 turns out not to be important just on its own, 0.0598. Well, there you go. Interesting. x4 doesn't really do much at all. We should talk about that p-value. We will come back to that in a second. Let's have a look at x3 on its own. Oops. X3 on its own, now that's a p-value. Look at that, 0.000576. X3 is highly significant, right? If you look back to the table where you've got them all in there, scroll back up, it looked like X3 was mighty unimportant, but then when you look at it on its own, it's mighty important. Now it tells you that if you only had x3, yep, you do pretty well in explaining why, but if you've got the other things, you don't need x3 on top of that. So that's what it's telling you, okay? And you can do the same for x1 and x2, and it looks like, from what we've just looked at, that x1 is going to be important on its own, but not when the others are in there. x2 is going to be important on its own, but not when the others are in there. Same for x3. x4 doesn't look as important, just even on its own, although I will say this. When you get a p-value of 0.0598, you're probably not going to be able to make serious declarations about anything, right? You know, this 0.05 business, it's a bit of a liars, damn liars, statisticians kind of thing, right? So do we really change our minds entirely if that number was 0.0498 and we say suddenly that x4 is really important? So this 0.05 threshold is not something you should particularly trust. It's a guide, and it's reasonable to say, well, it's almost important, right? A bit like me, I'm almost important. I'm like x4. So how do we get our hands around, or our heads around, what's going on here? Because it's clear that these variables are interacting with each other, and so teasing apart what's going on is pretty hard. Well, we can try to visualise the space a little bit, so let's try and do that. And then we're going to try something numerical, because visualising this space is a little bit difficult. So I'm going to load a package called Akima, and this package has a couple of graphical tools inside it that are useful. It has what are called perspective plots, and it has contour plot. Okay, so I'll show you the plots and then I'll talk through how you get them. So you need to load that library, and then I'll just draw the plots. So these are some pictures attempting to show you what's going on in this particular data set. Now, we've got 5-dimensional data, and so these are and I've shown you 2-dimensional plots. These are my best attempt to show you a 3D plot, right? I'm sort of stuck with a flat screen, so I've got to do this kind of thing. So these are 3 of the 5 dimensions. So I've got, this is x1, y is on the vertical axis, and the one that's going back here should be x2. Same sort of thing here, x1, x2, and then we're seeing the contours. So what do these plots represent? Well, it's a bit like, in the first case, this one here, it's a bit like looking at a landscape, right? So you're standing off in the distance, you're looking at the mountain, right, or you're looking over the plain, and you can sort of see, so it looks very steep in some parts. So the reason it looks steep here is where you don't have data, it can't produce anything, right? So it just drops down to 0. But where you have data, this looks like a plane, right? It looks pretty flat. It's angled, but it looks pretty flat internally, okay? So let's talk about this in terms of dimensions. So this data is 3-dimensional, right? That I'm showing you, 3-dimensional, x1, x2, y. But when I look at that picture, how many dimensions do you think there really are in the data? 2, right? Because a plane is a 2-dimensional thing, and I've got this plane sitting in a 3-dimensional space. So the data's living in a 2-dimensional space in this plane, right? But it's sitting perched into this 3-dimensional space, okay? And the contour plot tells you the same thing. So a contour plot's looking like a map that's got contours on it. So most people have had an experience in their lives of walking in the bush or on trails and so on. And you might have a map and you see contours. And you know when the contours are far apart, it's flat. You know when the contours are close together, it's steep, right? And so here you can see this is basically flat everywhere except at the edges where you run out of data. Then it gets real steep real fast. But that doesn't mean anything, you don't have any data. So this is again showing you that you've got a plane, a fairly flat surface. So sometimes looking at these sort of 3D subspaces of your original 5D space is a way to work out what the real dimension of your space is. It's a bit hard because we can't see 2 of the dimensions, but this is our best attempt. Producing these plots in R is pretty easy. As I said, it's in the Akima library, both of these functions. So the main functions are persp, stands for perspective plot, PERSP, and contour, okay? And the other stuff that's going on in this coding is preparation to get a grid over which you can get data. Because you've only got 13 data points, right? So the analogue that I'll tell you about this is you've essentially got this 3D space, you've got the 13 data points sort of sitting perched in that space, and it's like taking a tablecloth and throwing it over the top and just seeing it where it rests, okay? And so it rests on the data points, but the way the code works is it interpolates over some sort of grid, okay? That's the way it does the computations. So starting from the first line, I want to put both plots on the same page side by side, so that's where the MF row equals C12 is, okay? I want it to be occupying the middle of the plot, so I'm going to put a little bit of space at the bottom and a little bit of space at the top for a title. So I go OMA, outer margin, equals C4060. 4 lines of text at the bottom, 6 lines at the top, nothing at the sides. Okay, so these are just basically setting up my surface so I can put the plots on the page. Then in order to construct both the perspective plot and the contour plot, I need to take my data and I need to create an interpolated grid, and for that I use the interp function, which is what lives inside a schema. Okay? So interp, I give it the x's, x1 and x2, and I give it y. What it does is it creates a grid over which it computes an imputed value of y for each pair of x's. Okay? Then, when it can't calculate a value on the grid because there's no data, it puts an NA, a missing value. So what I do next is I come through and I just replace all those missing values by a 0, in other words a floor, so that it drops down to 0 at the bottom. And then I can just do pers. I don't really know why I've got divided by 200 here. It doesn't make any difference. You can take that out. Run it again. You'll see it doesn't make any difference. Same picture. Okay. And then I just title everything up. For the contour plot, the command is pretty simple. The command is contour of surf. So surf is this interpolated triple. Okay. For the perspective plot, you only give it the z value, the height, and it works out the rest based on what the x's and the y's are on the interpolated grid. The last thing I do is I just add the xy points to the plot. That's why you can see over here the points on the plot. If I didn't do that, they wouldn't be there. Right? So these are some graphics that you can use to kind of try and explore what's going on in 3D space. In this case, you've got a plane, right? So it's like throwing a tablecloth over the top and it just rests nice and smooth, right? Not all data does this. Well, let me show you a different example. You might remember early on we looked at the evaporation data. Okay. I'm just going to show you the evaporation data. Where is it? Show you the plots for that. I'm not going to go through the R code for it, it's boring. Just want to show you. That's, what's it doing? That's not, sorry. It looks like the same data as before. Okay, something's wrong there. Oh, object air not found. Oh dear. You go right to the top and do this properly here. Just going to show you these plots. There we go. So this is the evaporation data. So remember we had over 46 days we had air temperature, soil temperature, wind speed and those kinds of things. So this is an example where the data doesn't sit on a plane, it sits on a line. And so, you know, if you have a line that's going through 3D space and you throw a tablecloth over it, it sort of hangs on the line, much in the way your washing would. And that's what this is showing you. So it's sort of got this ridge running through. So this is what it looks like when you don't have that sort of nice planar structure. Okay, so again, I don't want to talk about the evaporation data too much here. I just want to show you that, you know, the shape you get tells you something about the structure of the space that you're in. And so you can see in this case it looks much more like a straight line in 3D space than like a plane. And you know, that's interesting because in 3D space I've got 3 dimensions to muck with. If it turns out that a plane is the right answer, then there's really only a 2D space underneath it, all that matters. If it turns out there's a line that's the answer, it's a 1D space. And that's what this is telling you. So that's what happens for the evaporation data. Now, I remember that just before we finished up, we had talked a little bit about coplots. I just want to show you very quickly, this is for the evaporation data again, what R's coplot function does. And really, the only reason I'm telling you this is to tell you not to use it, because it's a piece of crap, truthfully. So let me tell you what it does. See, what it does is it tries to condition on one variable and show you the relationship between 2 of the other variables. So, and you don't have a lot of control over the environment, okay? So the first thing it does, the variable it's conditioning on, so just by way of example, I'm looking at the relationship between evaporation and air, and I'm conditioning on soil temperature, okay? What it does is it takes the soil temperatures and it divides them into 6 different groups. Now, the first problem with R's coplot function is that it has a rule that you must have a certain proportion of the data in each group, so it allows the groups to overlap. and it only allows you to have 6, right? So there's no control. You don't get any control over that. Now, I don't know about you, but if you're a control freak like me, if R doesn't let you have control, you feel a little bit robbed, right? So it automatically gives you 6 groups, 6 conditioning groups, whether that makes sense or not. In this case, it doesn't. And they overlap. See how they overlap? Group 1 has values of soil temperature that go between here and here. Group 2 has soil temperatures that go between here and here. So this top panel tells you the co-plotting variables. And you can see that if you've got Group 1 and Group 3, you've actually got all the information that's in Group 2 automatically. So that's the overlapping. That's why I don't think that it's really all that sensible. So the idea is that this plot here is the plot of evaporation versus air temperature for that bottom range of soil values. Okay? This plot here is evaporation versus air temperature for that next up range of soil values, and so on. 3rd, 4th, 5th, 6th. So the layout is weird too. It goes 1, 2, 3, 4, 5, 6. I don't like it. And it doesn't give you control over it, right? In what world is it natural to go 1, 2, 3 and then back up 4, 5, 6? That's not visually very appealing, is it? You'd either want them side by side or vertically aligned. So the alignment's terrible, okay? So what are you supposed to do with it? Well, you're supposed to look from plot to plot and go, how does the relationship between evaporation and air change as the value of soil changes? But again, it forces you to move your eyes, first of all, left to right, then up, back to the left, and then across to the right again. You don't get a very good visualisation there. So this is very poor visualisation. So the benefit of it is there's this single command that does coplots for you, but they turn out to look bad and they don't tell you what you need them to tell you. So don't use them, right? It's weird, right? Because here's this perfectly good function that looks like it does everything you want, but it ruins your life instead, right? A bit like using Microsoft Windows. Yeah? You've got this beautiful laptop and then you put that thing on it and then nothing works anymore. Or Android, yeah? Same sort of thing. So don't use this function. You go, well, you don't often get people telling you not to do stuff. Well, actually, that's what people mostly do, isn't it? But anyway. Okay. All right, back to the cement. What are we going to do about this? How can we deal with this collinearity? All right, let's see if we can work out what's going on in this space. All right. So let me remind you, this is my set of heat evolved. This is my set of x variables. So what we've discovered so far by looking at pictures is that those columns of x are related to one another. So the question is, how related to one another are they? All right, well, a really simple way to do that, to look at that, is to just say, well, okay, we can look at a picture, we can see the relationship here. What other people like to do is they like to look at a correlation matrix. So this is a set of correlations between the different x variables. So this number here is the correlation between x1 and x1. Well, x1 is pretty highly correlated with x1, right? Always. So there's ones down the diagonal. But x1 has a correlation of 0.23 with x2. It has a correlation of minus 0.25 with x3. But it has a correlation of minus 0.82 with x4. So in other words, x1 and x4 are kind of twins. So high correlation means they move together, right? So they're like twins. They stay together, x1 and x4. And one way in plain language to think about that is when you get a correlation of around 0.8, if you've got one of the variables, you're probably not going to need the other one because they're carrying pretty much the same information, okay? So as soon as you see that, it's a bit of a flag that you've got an issue. Okay, x2. x2 is not really related to x1, 0.23, it's weak. It's related to itself, that's pretty good. Minus 0.97, right? Very related. So x2 and x3, they're like Siamese twins, right? Really, really joined. And look, is anybody surprised? Look at that. This picture screams that these guys not only know each other, they like each other a lot. Right? They stick together all the time. Minus 0.97. So that's what a correlation of minus 0.97 looks like, okay? not really related to x4, and then the rest you can see because we've looked at this half here. So you can see there are big correlations in here that give you an issue. So, okay, so the poor man's approach to working out whether you've got multicollinearity is to look at a correlation matrix and pick out the big numbers. And when you see big numbers, you worry. Now, this is the picture we've got here is pretty simple, right? We've got two big numbers in here that matter. These two, they're the same as these two, so we've got two big numbers that matter. And they tell you a pretty simple story. x1 and x4 are twins, x2 and x3 are twins. So maybe one way to go would be to drop out one of x1 and x4 and drop out one of x2 and x3, and that should be enough. Should be fine then, okay? So that's what the correlation matrix tells us. Now, if only life was that simple all the time, right? It just isn't. These are simple correlations. x1 has a twin, x4, and they move together. Right? Cool. Oh, by the way, everyone's quite happily nodding when I say they move together. It's got a negative sign. They don't really move together, right? They kind of move in antagonism with one another, but that's okay. They're still twins because x1 would be correlated as positive 0.82 with minus x4. So x1 and minus x4 are twins, okay? All right, so that's a simple story. x2 and x3 are twins, that's a simple story. Okay, life's good. Now, in real life, with bigger data sets and more complex data sets, it ain't necessarily that simple. For example, suppose I had 6 x's, x1 through x6, and suppose that x1 was not a twin with x4, but was a linear combination of x4 and x6. Now, you're not necessarily going to see that in a correlation matrix if there's a bit of noise around. So what you could see in cases where it's not 2 variables getting together and acting chummy, but 3 or 4 variables getting together and acting chummy, is that you might see correlations around, 0.5, and you start to think, oh, there's not much going on here. But there might be a whole lot going on, okay? And if you think about this in visual terms, the way we would look at this is we would say, there's obviously a relationship here between these two variables. These two line up. So if I looked at this in a 3D space where x2 and x3 were my variables involved, and I looked at that against y, I could actually reduce this not to a plane but to a line, okay? And so my 3D space collapses into a 2D space, right? And that'd be a nice simple visualisation. Problem is, if you've got a more complex relationship between the x's, that orientation is very hard for you to see quickly. And so the way we might typically do it, visually, is not necessarily available to us. What we could do is we could do a whole bunch of 3D rotating displays. We could rotate them around and sort of say, oh yeah, I can see that those points line up, that's cool. That might work. But that's only going to work if they pair up like this, and the patterns are really easy to see. But in more complex spaces, that's not going to work. And you can't go beyond 3 dimensions, right? So if you've got a complex relationship between x1 and 4 other x's, ain't nothing you can do in 3D space that's going to show you that. Because it's a 5D relationship, right? And 5D into 3D don't go. And so you have that problem. So there's actually a numerical technique which is designed to help us through this mess. So I'm going to tell you about that numerical technique. It's called principal components analysis. Okay? Now, let's be clear. I could probably spend 3 weeks talking to you about principal component analysis and you still might not get it. We're going to spend about 15 minutes on it. So you should expect not to get what's going on here. Okay? If you want to learn more about principal components analysis, there are whole courses taught in multivariate analysis. If you do applied statistics, anyone here doing applied statistics, Stat 3008, you probably hear about PCA? Yep. Nodding? Yeah, boring. PCA. Yep, I get it. If I was teaching it, no, that's not true. So we're going to spend the 15 minutes on it. Here's how to do it. Okay. Here's something really cool. I've got a couple of other websites that I wanted to show you. This is now relevant. This is a website by some people who've been trying to do visualizations to explain statistical concepts. This is really cool. So the URL is setosa.io/ev, EV explained visually. So I think this stuff is all done in d3.js. It's a JavaScript library. So they actually do some visualizations around regression, which are cool to watch. But they also do this really neat visualization around principal components analysis. So I'm going to try and use their website to explain it visually, and then we're going to talk a bit more mathematically. All right? So I'm going to start with a really simple example. This is a 2D example, right? Because, you know, it's great to have all this power to be able to take a 100-dimensional space and visualise it down into lower dimensions. But if we start with that, most of your heads will explode. And that's not good, right? Because, you know, Copeland Theatre is one of the very few lecture theatres we have left, and we don't want to have a big mess in here, right? If you walked around campus, it's pretty messy, right? Well, they decided we didn't need lecture theatres anymore, and so we're going over to Barry Drive and all sorts of stuff like that. So we've got to keep this place nice. So I've been told, don't cause people's heads to explode. Well, I'll try. I say to them, you are aware I'm teaching statistics. They go, oh, yeah, but just try and keep the mess down. Like, okay, I'll try. Okay, so we're going to start with a simple example. And here's the simple example. Really simple. I've got an x and a y. I've got two variables, an x and a y. There's the data. It's 5 data points, right? No one's head's going to explode over this one. This is going to be nice and straightforward. And I say to you, what does this look like? And most people, without thinking, would say it looks like a straight line, right? And then I'm going to say to you, well, okay, we started off in a 2D space. How many dimensions does this data really have? And most people would say, well, it's only got one dimension. And that one dimension is that straight line that I can see, right? A line is a one-dimensional thing and a plane is a two-dimensional thing, okay? And so I should be able to, through this relationship between x and y, turn this into a one-dimensional object. How would I do that? Now, visually, it's really simple to think about how to do that. Here's the line, right? If I want to reduce this to one dimension, what do? Rotate it. Huh? And then that second dimension's gone. There's nothing in the second dimension anymore, right? Nothing up here, nothing up here, or down here. Huh? And so that's what PCA does. It says, what's the real dimension of my space? I'm going to rotate this thing so that it looks like this. Now, you're thinking that's a really nebulous way to explain what PCA is doing. Underneath the hood, what it's doing is it's saying, okay, here I have two dimensions. In dimension 1, x, there's a certain amount of variation. Okay? See? The data goes from here across to here. So there's that much variation. Right? Okay. What about in the y direction? How much variation is there? Well, there's a fair bit. It goes from down here, about 3, up to here, about 7.5. So it's that much. So that's how I know this thing's a 2D space, because it's got variation in one direction, it's got variation in the other direction, and so it fills the plane. Right? Okay. Now, when people say to me, okay, I don't think it's really two-dimensional, there's a line through here and the line's one-dimensional, what am I really saying? I'm saying, well, okay, why don't I rotate this thing so that in one dimension, all the variation is there, but in the other dimension, how much variation is left? None. Right? Perfect world, none. Okay? So I've rotated it. Now this collapses from being 2D to being 1D. There's no variation in the vertical direction, all the variations in the horizontal direction. So, in mathematical language, what is PCA doing? It's saying, in the two-dimensional space that I've got, find me the one-dimensional subspace with maximal variance. Okay? That's what it's doing. Find me the one-dimensional subspace with maximal variance. Then, find me the orthogonal subspace to that one-dimensional subspace I've just found, and find me what the variance for that is. If the variance for that is close to 0, I've managed to reduce the dimension of my problem. Okay? So, PCA is a rotation to find the maximal variance subspace of this 2D space, and then the other dimension, it'll have a variance too. It's got a little bit of variation, not a lot. And if that second variation is close to 0, then I'm good to go.
and I've got dimension reduction. Okay? Now, what is that subspace? Is the next question that you might ask. That subspace is the line y equals a plus bx, the one that was fit, right? Y equals a plus bx. You're saying, well, it's still got two things in it. It's got an x and a y. Okay, create a new thing, call it z. Z is y minus a minus bx. That's a new thing. That z is the only dimension you care about. Okay? And that's your one dimension going forward. So, that's what it's doing. All right, now, if it was only good for two dimensions, no one would use it because we've all got eyes and we can all see very easily what's going on. So, what this example now does is it moves into three dimensions. All right, so now I can't show you three dimensions on a 2D screen, so I've got to resort to these kinds of things here. So here's my data. So they've done this really beautifully. I've got a point cloud. It's rotating here. You can see my xy, sorry, my x1, x2 is that plane that's got the hash on it, okay, and then the y's are the heights, okay, and you can see I've got three colours, the primary colours, red, blue, green, and those are my primary axes, x1, x2 and y, okay. Now, this is 3D data, right? It's rotating in 3D space. Everyone sees that as a 3D thing, right? Yep, okay. So the question is, can I reduce the dimension of this? And let's think about it. What do you see when you see that picture? Do you see 1D, 2D or 3D? Maybe 2D, yeah? It sort of looks like there are certain dimensions where this thing's very variable and dimensions where it's less variable. You could imagine rotating this so that you're sort of looking down the barrel of that thing, a bit of curvature to it, but you're sort of looking down the barrel of that thing. Okay, and so if I click on Show PCA, what it does is it says, okay, what dimension, what direction is most variable in this picture here? And most people will say, well, it's that one, right? It's that one. You can sort of see it. It's moving, so you've got to wait. That one. And it moves again, like that, right? So that's here. So that's the direction that becomes principal component 1. The most variable direction in that 3D space, according to this data. Okay? What about the other two directions? Well, the second one is kind of captured by a circle, right? Because you kind of got, it looks like a tube. Maybe it looks a bit like a sausage, right? Like you get at Bunnings. Anyone here go to Bunnings? No, you're too young. You're too young to go to Bunnings. Oh, well. I go to Bunnings on the weekend and fantasise that I can actually do stuff. And I buy heaps of stuff because Bunnings indulges my fantasy, and then I go home and destroy stuff. It's really good. It's really good. Then I go back to Bunnings to find the stuff that will repair what I've just destroyed. It works out really well for Bunnings. Oh well. So it looks like a sausage, right? Looks like a sausage. Well, it looks like 3 puffs, but if you put skin around it, it'd look like a sausage. And there's x1, there's your first principal component, and x2 and x3 have much smaller variance. Now, these things over here at this side, they show you a before and after. If you just use your original variables, your 3 original variables, you can see there's roughly the same variation in each direction, okay? Just in the original shape, they're sort of spread like that in each direction. If you say, what's the most variable single direction, you can see you get this much variation, goes between roughly -5 and 5, but then the other two directions kind of collapse, right? Very small amount of variation in these other two directions, okay? And so you've got here dimension reduction from 3, probably down to roughly 1, where you've got 1 really variable direction and then 2 not so variable directions, okay? And then I've got a bigger and bigger and bigger example, which we won't bother going through. You can have a look at it if you want. All right, so how's that going to work for our data? Well, let me show you in R how this works. Now, we're going to do a little bit of prep, and I'll tell you why. When I talk about these directions, I have in mind data that has sort of consistent spread between each of the 3 variables. Okay? See, if x1 was measured, so let's suppose these are all chemical constituents of cement. So these x's have pretty much the same scale, right? They're all roughly the same kind of variation. But you could imagine a data set where x1 was measured in billions of dollars, and x2 was measured in litres, and x3 was measured in, I don't know, what's another unit of measurement? Kilograms, and so on. Different variables with different units. And there's nothing that says that they have to be equally variable, right? So your perceptions of variability when you look at a plot are going to be controlled by the scale of the data. So what we typically do before we do a principal components analysis is we standardise each of the variables, okay? We centre them so they have mean 0, and we scale them so they have internal spread 1, okay? So centering them is easy. I take my original x and I subtract out the means of each column. Now, that sounds like an easy thing to do, right? Take each column of x, subtract out the mean of the column. How would you do that in R? There's this really neat way to do it. You could do it boring way and go, you know, x1 minus mean x1, right? But that's boring. I don't do things the boring way. This does it all at once. So let me show you, and this is some cool R code. So you take x, which is a matrix, okay? What we're going to do is we're going to sweep. Sweep is a function that says subtract out. So we're going to sweep out or subtract out from the second dimension of x, the columns of x, whatever this third argument is. So we're going to take each column of x and we're going to sweep out or subtract whatever that third argument is. The third argument is what I get if I take the x matrix and I apply the mean function to its columns. So apply x2 mean, takes each column of x and calculates the mean. All right? And then I sweep that out of each column. So the first column of W is x1 minus the average of the x1s. The second column is x2 minus the average of the x2s, and so on. Okay? So this first command here takes the x columns and subtracts out their respective means. All right? The basic function to do principal components in R is PRComp. PR, principal, comp, components. All right? So PRComp is the basic function. And what I want to do is I want to do that on a standardised version of the x's. So a version of the x's where the mean has been swept out of each column and each column is divided through by its standard error. How do I do that second part? I take my x's that have had their means removed and I divide by 1 on the square root of the cross product of the matrix. Okay? So these two lines here basically sweep out the means from each of the columns of x, divide each of those resultant columns by the standard deviation of the column, and then use PRComp on that. Okay? Now, okay. If you love R, then you just love what I just said, right? Because you're going, wow, that's cool. In 2 lines, you did something that might take me 3 weeks to code up. That's fine. What I'd encourage you to do is think about how you might do that the slow way, right? Because coding doesn't have to be, you know, I'm smart and no one else is. Coding can be, well, I want to take each column and subtract out its mean. I want to take each column and then divide through by its standard deviation. Think about how you might do that, right? I mean, you can do it longhand pretty easily. So you might go Z1 equals, you take x, column 1, minus mean, minus mean, oh, is that a minus? Oh, it is. X1, right? So your Z1 is that. Z1 equals Z1 divided by standard deviation of X1. Right, that'll do the same thing, and that'll create... there is no standard deviation function. For shame, Michael, what are you thinking? Square root of variance, that's what I wanted to do. You see, you take 2 weeks off and you forget everything. It's just weird like that. Okay, I almost forgot where the room was today. Where am I? I was almost over in Barry Drive. Who knows? Okay, so you can do that. You do that for Z1, do the same for X2, do the same for X3, do the same for X4, and then push them back into the matrix, all right? People are squinting, so let me do it properly.
So that, let me do it properly. There's Z1. Okay, then I do the same for Z2, right? Boom, boom, boom. I'm just showing you how to do it the slow way. Okay, Z2. Okay, then do it for